So hello, let's start off with the band breaks. So band breaks we'll do of two varieties. So one is a simple one, which you can see in this figure here. So this is a simple band break. You may remember this from the previous classification. Here. Yeah. So this is a band break, which is a simple type, and this is band and block break. So both of them we are going to cover together. So let's dive into this. So band break and block break. So the first variety of band break is also called as a simple band break. Right? Right. So this is the one. This is the simple band break, which you can see here in white, and the one which you see below is band and block. So this small block which is kept aside, separated from the main link, that is called as the band and block break. So, but the working principle is pretty straightforward. You can see the pressure P or force is applied, where point B here will be rigidly fixed here, and point O is the one with the pivot. So pivot point, and this you have this is similar to a belt kind of an arrangement. You can see T1, T2. So these are tension in the tight side and slack side. If you remember the first unit, which was belts, right? So we're carrying on from that unit. You have T1 and T2. There is a tension on tight side and the slack side. Right? So this is equal to, like, you can consider this as a belt kind of a thing. And uh, we'll do the derivations. There is the force derivations of all of them. But first, the working principle. So this usually consists of a steel strip here. Okay, a steel strip inside which you have a friction line lining inside of the steel strip. Usually you have a lining of friction which is pressed against the drum. So this drum which you can see here, as usual in all the brakes you have that drum. So these drum will be rotating, and the objective for this steel strip is to bring it to rest, okay, by pressing against it. Okay, sometimes this band brake is used in a self-lock condition. So if you remember before, I told you there are three conditions where brakes are applied. That is self-energizing, self-locking, and grabbing. So sometimes the self-locking property is useful. Most of the time it is undesirable effect, but sometimes it is useful where you can prevent it from rotating in the opposite direction. Okay, so that's where this kind of brakes are used. Okay, so that's it. So like backstops, instead of rotating in the opposite direction, you can stop it on that. Mostly these are used in hoisting of materials, heavy equipments, those kind of brakes, lifting kind of applications. So this is the first category. We're going to derive this, and the second part is the band and block. Okay, band and block. This is just a simple band break. There are two varieties. So we'll solve two numericals, and we have derivation of this. So the notations used, the figures which you see on the right, these are taken from your data handbook. So F is the force on the right side end of the lever. So this point usually will be pivoted, and on the opposite end, whatever the effort you need to put on the lever so that you have the braking action, that is force F. And F1 will be force on the tight side, or you can say tension on the tight side. So just like belts, tension on tight side and slack side. Okay, low side on high side, can categorize like that. F1 and F2, and Ft is tangential towards you, that is away from the screen. Theta is the angle of lap, so just like the belt drive, right? So you can see the steel strip being engulfing the drum here. So whatever angle it is engulfing, that is called as theta, usually in radians and stuff. So that's theta. Then P is this pressure intensity. So that's small pressure intensity which is applied by the steel strip onto the drum while the braking action is taking place. B, width of band, that is perpendicular to this direction here. D is the diameter. H is the band thickness. So the steel strip along with the friction material will have a thickness, that's the H. And sigma D is the design stress. How much stress usually depends on the material of friction material. So these are all the notations which are used for deriving and also for problem solving kind of application. Right. So we're taking from this particular figure here, force F1, F2. First, we'll derive the force required to engage the brake or braking force. So braking force required to engage this brake. You check it out. We have this figure. So we'll start off with this figure. So usually there is a small mistake here. This B is not inclined like this. So this is just the linear distance between these two portions. Okay, you can assume this to be infinitesimally small, and this distance B is linear. So let me make a small change for you. Okay, this here is B. This is B, not this. Okay, so this is B, the distance, the linear distance, and this entire thing is A, and you have F1, F2, and it's rotating in clockwise direction. Right. So let's derive for this. Right. So let me start off with the derivation here. So we'll start off with the band tension. The the ratio of band tension the ratio of band tension is given by F1 over F2 equal to E power mu theta. This is given equation 13.18a. Okay, this you might remember this equation here. So this is taken from the ratio of belt tension from belts. That is the first module. T1 by T2 equals E power mu theta. Mu here is coefficient of friction of this friction lining here, and theta is the angle of lap or angle which is engulfed here. Really, I think this particular area. Okay, angle that it is engulfed, maybe in this fashion, somewhere that till here probably. So this entire area which it is engulfing. So that is can call that as theta. This angle here. So that's theta there. This angle of lap, usually taken in radians. Right. Also, tangential force Ft is equal to F1 minus F2. This is also given equation 13, 18, B. Okay, tangential force is tension on tight side minus tension on slack side. So this is what you can do F1 and write it in terms of F2. So using this equation here, send over the F2, then you'll get e power mu theta F2 minus F2. That means you can take this F2 common. Then you'll get in the inside that is e power mu theta minus 1. Okay, so continuing here, we can just write F2 in terms of Ft, that is Ft, that is tangential force over e power mu theta minus 1. Right. Okay, so that's F2. There is tension on the slack side. So continuing from the first equation which we have written, we can note that it is F1 is F2 e power mu theta. This we can modify. Let's just plug this F2 here. So F1 will be equal to Ft. Instead of F2, we are writing this e power mu theta over e power mu theta minus 1. This is also given equation 13.18. You can just write in a sequential manner 18.1a, 18.1b, and 18.18. Oh, so 0.18c. ABC, you have a continuity in equation. So just by looking at the data handbook, you can write these equations. Now also, we'll start off here in the next part. So objective of our objective is to find the force F. So we are not given the relation to the force yet. So let's continue. So we can find this relation from moments, obviously, from looking at the diagram. Right. So let's do that. So the torque. So the torque T, or you can also write MT. Okay, T is what is given in the red handbook. Absorbed. Absorbed by the brake is T equals. So this equation also I think you might remember from belts. This is F1 minus F2 into D by 2, where D is the diameter of drum. So in the previous case it was R, I guess, when we did for the belts, for the pulley and stuff. So now let's link this to the moments. Now taking moments, about there is a pivot point, and then for clockwise. For clockwise, so let's go back to the figure. So if you notice F, and it is at a distance of A and is inducing a clockwise movement, we'll take clockwise as positive. Okay, and the another force which is acting here is F2, which is trying to pull it above. So this is trying to move this about point O, about anti-clockwise direction. So F2 is negative times the distance B, and F is positive at a distance of a. Here F1 isn't acting because it is fixed. It's acting at the pivot point, so therefore its reaction will be 0. And by the way, we are taking moments at O, at the point O. So noting that we have minus F2. So F2 being in anti-clockwise movement, F2B plus, and the force F is now trying to pull it on the clockwise direction. So F2A is equal to 0. No other force is acting. So now we can write it in terms of F. So F equal to is F2B over A. So F2 we can substitute whatever we got from the previous equation. So this is what is F2? Yeah, this one here. Substituting this, you get Ft B over say e power mu theta minus 1 into A. So this is equation. This is also given in equation. So 13.18 G. So this is the equation for clockwise uh, motion. Suppose we take the same thing in anti-clockwise direction. So let's say for counterclockwise or anti-clockwise. In that case, if we take it about O, no, we can't take it about O here. We will take about this point here, point 3. In that case, it will be minus F1 B plus F into A equal to 0. So it will be F equal to F1 into B over A. Now expanding this F1 in terms of F1, it will be Ft into e power mu theta times B. This is substituting F1 here, and this is e power mu theta minus 1 into A. So this will be equation 13.18 H. Right. So these two equations here, so these two equations, you can just mark them. Oops. We'll be using these two for clockwise and counterclockwise direction. Force required in both the cases for simple band break. Okay. So this is for simple band breaks. Let's go for the differential. Differential, or you can say as a band and shoe break. So this is for the differential or band and shoe. So this small part here, band and block. So this small part here is called the block. We can also write this as a differential. Differential band break or a differential band break. Now for this we can just take the equations from the previous, but we'll take moments about it. So summing of moments about action O and equating them to 0, and this will say for clockwise direction. So check it out. Force F from O is trying to create a clockwise, so it is positive. Let's say F into A, and force F1 is trying to pull this point here, again inducing a clockwise moment. So that also can be written as positive f1 into b1. So that's the distance here, b1. I can take it as a linear distance. Assume this part is straight, and finally this point here, f2, which is trying to move it in anti-clockwise. So therefore, that is negative f2, and at a distance of b2, equated to 0. So therefore, f here will be f2 b2 minus f1 b1 over a. Okay, so we'll keep this as it is. Next, continuing from the previous derivation, you can extract the data for f1 here. So write it in terms of f2. So f will be f2 into p2 minus, instead of f1, right? So we can write f2 e power mu theta. Remember from equation, f1 over f2 was equal to e power mu theta, right? So we are extracting it from that to b1. So b1 as it is, whole divided by a here. So that's equal to, you can take f2 common, and you have b2 minus e power mu theta, again b1 over a. So now we can replace this again, f2, you replace it by ft in terms of tangential force. Okay, so there again there might be a distinction. So let's say f. So this is the actual equation which you have in the data handbook. Ft in terms of from the previous derivation, if you just note. So ft, you combine that, will be b2 minus e power mu theta b1 over e power mu theta minus 1 into a. This is taking into account the previous derivation. This is in 13.18e. Okay, so this equation again useful while solving the numerical. Right? So same thing. Let's take moments from taking moments about anti-clockwise direction. So taking summation of moments about O and equating it to 0 for counterclockwise direction. So check it out here. So f1, that is f into a, that is again clockwise is positive. f1 f2 into b1, and that's positive. So essentially you get the same thing. Doing that, you have f to a plus is counterclockwise, right? This f2 to b1 minus f1 into b2 equal to 0. So now we have f, which is f1 b2 minus f2 b1 over A. So simplifying further, so now you substitute for F1. In the previous, I think you substituted for F F1 only. The same thing here also. So this is e power mu theta into F2 B2 minus F2 B1 over A. Now taking out F2 here, you have e power mu theta B2 minus B1 over A. Now F is equal to Ft, instead of F2, no, substituting again Ft, again e power mu theta B2 minus B1, no change here, over e power mu theta minus 1 into A. So this will come to equation 13.18f. So these two equations we'll be using by solving the numericals. So this in this case, the anticlockwise one, here self-locking is not positive. Okay, in this kind of a break, which is running at anticlockwise direction, just make a note here. So note for counterclockwise, self-locking is not possible. Self-locking is not possible. Okay, as e power mu theta and B2 is always greater than B1, is always. So B2 will be always greater than B1, right? So therefore, in counterclockwise condition, it cannot be possible. So that's where we take the self-locking condition only for the clockwise one. So let's continue from this point. Take this here, right? Okay, so this is for self-locking condition. For self-locking, as I told you before, it is desirable only when you don't want the wheel or drum to move in the opposite direction. So as one which you intend to do. So for self-locking, the force F should be equal to 0, essentially, or even negative. It should be 0 or negative. So this will happen when P2 is lesser than or equal to B1 times e power mu theta. Okay, as given in for clockwise condition. So that means B2 by B1 should be lesser than or equal to e power mu theta. Right? So this condition should be satisfied. For self-logging condition, whenever given in the question, you need to consider this clockwise condition and only find for this value here. That once it satisfies this equation here, only then you are supposed to use that B1 and B2. Okay. So yeah, that's it for the derivations.